Today we have with us Steve Connor, who will be our presenter. And Steve Connor has been with us for over 40 years in the industry and is the Director of Training at Cleaver Brooks. And he will have probably 40 to 45 minutes on this topic, with about 10 to 15 at the end for questioning. We do have an expert panel that is available at the end to take these questions. And again, you'll use your Q&A tool on your WebEx control panel. I would also like to let you know that this event is being recorded and will be archived on our website. You may be able to access the webinar at www.cleaverbrooks.com/webinars. And not only will we have today's topic there, but we have archived events and information about our next topic for next month, which will be meeting the industry's large steam demands. I'd like to go ahead and control over to Steve Connor. So Steve, go ahead and give us the straight talk about boiler efficiency.
Well, Susan, I appreciate that. You can see, obviously, we're talking about efficiency today. And quite frankly, the reason that we chose this topic is because there's a tremendous amount of confusion out there on this subject. You would think there wouldn't be, but there actually is. And confusion is about the terms and what they really mean. For instance, we hear the term combustion efficiency being used when, in fact, the individual is referring to thermal efficiency. Here, boiler or fuel-to-steam efficiency. In fact, one is referring to thermal energy or thermal efficiency transfer. And this just goes on and on. So this session today is to establish some clarity about these terms, what they really mean, how they're arrived at, and what will negatively impact high efficiency performance. Now we'll talk about ways of determining boiler efficiency along with ways to improve it by supplying the most cost-effective system for delivering steam or hot water to the process or to the space for heating, comfort heating. Just remember one thing as I go through this presentation today, that when we burn fuel in a boiler, we're burning cash, which if it's needed to be wasted, will cost the business a lot of money on its bottom line. So keep that in the background. Boiler efficiency, we can really boil it down to these basic terms. We have combustion efficiency, we have thermal efficiency, we also have fuel to steam or fuel to water efficiency if it's a hot water boiler, and also the same as boiler efficiency. So we could say that boiler efficiency and fuel to steam or fuel to water efficiency are synonymous terms. The last one we have, which has come out recently, which is a good way to evaluate boiler efficiency, is termed in-service efficiency. So we'll be going through those and determine what they really mean. If we start with combustion efficiency, actually combustion is a chemical process. As it starts with a fuel which is primarily carbon-based. It could be natural gas, it could be oil, which has hydrogen in it. We have within that fuel, we've got possibly some sulfur if we're burning oil. We have nitrogen. Combine that with the air that we breathe, right, for combustion, which contains oxygen and nitrogen, by the way, is about 78% of the that we breathe that we use for combustion. And quite frankly, that goes along for the ride. It does nothing as far as oxidation is concerned. So then we have a burner. These elements, the chemistry on, oxidation occurs, and when that oxidation occurs, what we get is heat that comes out, the BTUs, some CO2, carbon dioxide, some will refer to as the global warming gas. We have water, and we have carbon monoxide, possibly. We try to keep that to a minimum, and we'll talk about that later. We might also have some nitrogen oxides and some oxides upon the fuel. These are emissions that come out of this oxidation process that we have to contend with. So the burner itself is a combustor. It's these elements And this one that actually is the catalyst that gets this chemistry going. And for it to occur, we have to have time and turbulence. That's what's going on with that burner. The temperature, of course, is supplied by a spark that ignites a pilot, which ignites a main flame, which then, through spontaneous combustion, the ignition continuously occurs. That also provides turbulence so that we can mix this fuel and this air together to give us good oxidation. But the question is, what gives us the time? We need the three: time, temperature, turbulence. What gives us the time? Well, that furnace. What you're looking at right here is an air tube boiler, and I'm looking at it from the rear. The rear door is open, and you get a gentleman here in the front that's inspecting the refractory around the burner throat. So this particular furnace to be properly designed and mated with the burner to give us proper oxidation and full combustion, efficient combustion. I have to be concerned about the flame shape so I don't impinge on these walls and cause a cooling of the flame, a rapid cooling of the flame that could generate carbon monoxide, CO. I have to make sure it's properly matched. And what I'm trying to do here is take advantage of this radiant heating surface. Look at radiant heat transfer. We're talking about things like emissivity, talking about the theory of Stefan Boltzmann, who looked at radiant energy and how effective it can be if properly employed. Remember, we've got a huge delta T here. You've got temperatures in this furnace which are over 2,000 degrees. We have water side temperature on the other side that might be in the 300 degree range or less. Tremendous delta T. And as a result, the heat transfer is very, very extreme, and we want to take advantage of that. And that's things that boiler designers today are doing, is trying to take more and more control and more advantage of radiant heat transfer in the furnace. But when everything is said and done, that furnace, its geometry, its length, its diameter, its configuration, its volume, will be the time. To be able to achieve 100% combustion efficiency, I have to burn every single molecule of fuel. I have no excess air. I'll have no hydrocarbon. I'll have no CO. That is called perfect combustion. If you want to put a number on it, it's 100%. Metric combustion. But you're not found in the field. We do it in the field. We don't set it up in the field that way because it could be dangerous. We start to go fuel rich. We don't have proper control. We have what we call a fireside occurrence in this business. And the reason for that is variances in the atmosphere that we have positively no control over. The temperature of the room, which is our combustion air. The barometric pressure, which can rise or fall. The humidity, the calorific value of the fuel. All these variables make these burners up at something less than stoichiometric. We've got to go air on the conservative, so we add additional excess air to keep us safe. So what's excess air? Well, nothing more than that percentage of air above the stoichiometric. 1% combustion efficiency. Remember, when we talk about combustion efficiency, we are only talking about the effectiveness of that burner to properly oxidize the fuel, the air, and combust. So when we talk about excess air, it's that percent of air, that volume of air, which is for stoichiometric combustion. Let me show you a curve. If you look right here where this red arrow is and my little red dot, here is 100% efficiency, stoichiometric combustion. No excess air. On here, I've got no CO. I'm burning everything. Stoichiometric combustion. The way we set these burners up is to air on the right side of the curve in order to give us that margin of air. Don't go fuel rich. Have a post-combustion explosion in our furnace. So you can see here as I go to the right of the curve, here's 100%. is approaching 20% excess air, of course, my oxygen is increasing. This line here is showing me my carbon dioxide, the CO2 level. If I combust any carbon-based fuel, I'm going to give off carbon dioxide, CO2. If a falls in a forest and it decays, as it decays, it gives off CO2. Anytime we're involved with carbon and it disintegrates, we generate carbon dioxide. Now, here I'm burning natural gas. The CO2 value at stoichiometric is going to be in about the 11% range. That's as high as I can go. If I was burning number 2 oil, it'd be around the 14% range. But I'm burning natural gas here. So this is my CO2 level. As I go to the left of the curve and I start to go fuel rich, you can see what's happening to my CO right here. It's to increase. Got to be careful about that. Let me show another curve. Here you see, this is the inverse of what I showed you before, but follow me now. This 0 here would be essentially 15% excess air or 3% O2. They're synonymous. We can talk about these terms interchangeably. 3% O2 is the same as 15% excess air. This we would like to most of the time. If they can hold 3% O2, 15% excess air, that would be just great. But what does it really mean? Well, if I take a look over here, where be at 1 combustion efficiency, essentially added 15% excess air or 15% more mass to the overall oxidation, to the overall mass of gas within that boiler itself. Okay, that's what I'm doing with this excess air, 15% more. Now, we see a lot of in the field today, our boilers operating in this range, 7% O2, 45% excess air. Not at all uncommon. And so that is essentially done. Well, from 3% excess air to 7% excess air, I've increased it 4%, and through the math and the computations, I've lost 2% in all efficiency. So I'm going to hold here, but finding out there is a lot of this needless waste of energy, and it gets involved with combustion. Now, all that combustion efficiency, I suppose you could, but that's really going on. So what we're saying here, when we talk about combustion, we're talking about 100% combustion or 95% combustion efficiency. You can hold 3% O2 at the time when you're firing and handling load. We get very effective combustion, good combustion. Now, if I show you the curve here, here you see a firing rate of 10% to 100%. With most boilers today, up there are some differences now. There are some differences to this. Most boilers, when they're operating in the range, which is in the 60 to 70% range, this is where you're going to find a lot of them. And you see at this particular point, I'm about, 4.5% O2, 25% excess air. This is where you're going to find a lot of boilers. There are boilers out there today that'll be able to hold pretty close to that 3%, even in this operating range. Now, this operating range of 60 to 70% gets very, very important as we talk about something else a little bit later. So keep in mind. To realize here is that as you decrease in firing rate, excess air will increase. More in some units, less in others. Certainly something that you engineers ought to keep in mind, especially as it relates to how you size boilers for load. You don't want a boiler hanging in this area all the time. I mentioned before that there's variables that we have no control over. One of the biggest threats that we have to good, safe, and good efficient, or even combustion, the temperature in the room, the ambient air, the secondary air that we use for combustion. What we did is we set this boiler up. It was 80 degrees in the boiler room. Barometric pressure was 29 inches of mercury, and we set up at 15% excess air, which is 3% O2. Uncommon, especially down south in summertime. That in the boiler room creeps to 100. You've got no control over that. Or 120. Look what happens to my margin of error. 9.6, 1.1. I'm getting close to stoichiometric here. The other way, I'm blowing that out the window, right? 78% of our air, where I go from 80 degrees to 60 degrees in that boiler room here in Milwaukee. The air is denser, it's colder, it's denser, and as a result, my excess air increases. I'm just heating that air and blowing it out the stack. So what's that? This is where an O2 trim system can really help. If you have a boiler room then temperature and you've got no control over it, and or you've got a boiler that modulates a lot, especially one with single point positioning, a lot of linkage, good candidate for O2 trim. If the boiler room doesn't vary in temperature, if it doesn't modulate a lot, it costs the money. Now, it's very important to keep in mind when we're talking about combustion, is applying the proper amount of air for that combustion process. And a good rule of thumb that we've used over the years is 10 CFM per boiler horsepower. That, of course, is to support the combustion process, to oxidize the fuel. CFM is used for ventilation. Now, that's not to keep the boiler operator comfortable. It's really to make sure that that room not go negative. Take that, let's say a 300 horsepower boiler, we need 1,000 CFM of air. You divide by 250, and then you get the cross-sectional area in the room that we need for ventilation. Let's move on to the next easy criteria that we would like to define, and that's thermal efficiency. What thermal efficiency is, it's nothing more than the ability of this heat exchanger that you see right here. Here's my burner. It's into the furnace. That's the area right there, as you can see, in the furnace. And then I've got these convective passes. This fire tube boiler has these tubes. The hot gases are going through it. When I talk about thermal efficiency, I'm only talking about the ability of this heat exchanger to absorb the heat. To get heat, put it into the water and generate hot water or steam. That's all I'm talking about. And of course, that energy is going to vary as I turn the burner down. And I can have 4-to-1 turn down, I could have a 10-to-1 turn down, I could have a 20-to-1 turn down burner. It's all about the amount of energy going into that unit, then absorbed by that heat exchanger so it goes into the water to make hot water or steam. It does not consider radiation and convection losses. Okay? So it means that those radiation and convection losses are lost somewhere, not going into the water, or hot water. Keep that in mind, we'll address it a little bit later. One of the things that manufacturers and designers are doing today to improve the overall convective heat transfer in the boiler, to that transfer increase the overall thermal efficiency, is add extended surfaces inside of those tubes to break up the gas, to get away from the laminar flow, which increases the Reynolds numbers, which is nothing more than a ratio between inertial and viscous forces. To increase the Reynolds numbers and also the heat transfer coefficient, which is the heat flux ratio against delta T. That's all the technical jargon that goes on, but essentially all I'm trying to do is break that gas up so I've got good contact with all surfaces on the heat transfer side of that tube to get it into the water. And now what I can do is reduce the heat transfer surface by as much as 85%. Why do I want to do that? Well, I can put more energy into the furnace, number one, reduce the convection section, and reduce the overall size of this, let's say, horizontal fire tube boiler. That's why the industry is beginning to gravitate in that direction. So thermal efficiency. About fuel to steam or fuel to water efficiency. Here, what you have is the net amount of BTUs that will be going to the process or going to heat the building, okay, the hot water to heat the building hydronically, in net of radiation and convection losses. We look at various boilers. Convection losses can differ anywhere from 0.5% to 2%. In other words, in a large fire tube boiler like this, it could be 2%, 1.5%. On a small little vertical fire tube like this, might be 0.5 or 0.75%. Depends upon the mass. Remember, when we measure radiation and convection losses, and the reason I mentioned turn down before when I talked about thermal efficiency, it's all based on input. So the fact of the matter is, when measuring radiation and convection losses, they get larger as input decreases. What would that be? Well, the reason is mass within the boiler itself. Let's say that we're operating at 100 pounds. The saturation equivalent to that is 338 degrees. Well, regardless of where I turn this burner down, regardless where I turn it, that temperature is not going to change. So I decrease the firing rate, therefore the input, I'm biting into an ever smaller number. So therefore the radiation and convection losses climb inversely to input. All right. Boiler is rated. That's the question. Keep in mind, when we as boiler manufacturers and producers are boilers, what the engineer starts with is catalog or end data. And we're going to catalog that boiler saying it's a 100 horsepower boiler. Well, that's based at full fire, at 0 gauge pressure, okay? All 14.7 pounds at sea level, so my gauge is reading 0. Feed water, keep in mind, is only 212 degrees. Now, how many boilers out there are fed with 212 degree water? But we base the sizing of these boilers initially. And there has to be smart enough to be able to make accommodations accordingly based on the load or what he's heating or what the process might be or so on, and size the boiler accordingly. The water temperature or the operating pressure is going to be more than that, and obviously it will be. What else do I have to be aware of? Well, when we're looking at boiler efficiency and how we're doing, you remember that you have to benchmark the information that you're looking for. So that we're looking at the stack temperature coming out of that boiler. The stack temperature in an efficient boiler is going to run anywhere between 50 and 100 degrees above the saturation pressure or temperature based on pressure. So looking at efficiency, we want to evaluate it. The first criteria we have to look at is what's the operating pressure, because that's an equivalent temperature. More importantly than that even, it's the firing rate. Low fire, medium fire, high fire, when that temperature is occurring. What's the ambient temperature in the room? Is it 100 degrees? Is it 60 degrees? It's going to add to the gross temperature of that stack. What's the feed water temperature? What's that boiler? 112? No. 180? Could be. 127 coming out of a deaerator? Could be. All right, what else do you have to be aware of? Once establish that benchmark or those benchmarks, now I have something logged in my boiler room log that says that my steam temperature is now 395 degrees. I'm operating at 100 pounds. The next day you come in and my firing rate is high fire. Temperature in the room is 90 degrees. My feed water temperature is 180. You boom the next day or later, the criteria is all the same, but my stack temperature has gone up. Cost you 1% in fuel to steam efficiency. And what is that? On the fire side, selling on the water side, I'm in the heat transfer across those tubes, whether it be a water tube or a fire tube. So this thing is to make sure you've got a very reliable stack thermometer in stack, and you very conscientiously log temperatures against pressure, firing rate, ambient temperature, and feed water temperature. Very, very, very important. Because when you see something like I'm showing you right now occur, what's gone on with that boiler? And 9 chances out of 10, it's the water side of that boiler or fire side. It's either gotten fouled from soot or scale. Another example, follow me here. At 220 degrees is my flue gas temperature. I've gone to 260, and you can see right here in the numbers, I've gone from 84% to 83%. I've lost 1% based on that 40 degrees. Now, here's something else that's really interesting when I talk about the confusion in terms out there. This is really a fuel to steam or a thermal efficiency chart. But look, call it combustion efficiency for natural gas. It has nothing to do with combustion efficiency, really. We're either fuel to steam or fuel to water or possibly a thermal efficiency. If radiation convection losses are included, it's thermal. If that is, it's steam. So that's how this confusion is promulgated. All right. I talked about feed water temperature. Let's just take a look at this particular chart to see what I mean. When we manufacturers catalog our boilers, it's from a 212-degree feed water, 0 gauge pressure, and 34.5 pounds of steam per hour per boiler horsepower. Drop that feed water temperature to 100 degrees, keep my washer at 0 gauge, like 0.9. If 100 pounds of operating pressure, I'm at 112-degree feed water, I've lost a little bit, 34.5 to 33.2, because of the operating pressure increase, more BTUs required for sensible energy to get that temperature up so I can start to apply my latent energy. That's it is. But anyway, look at this drop because of 100-pound operating, 100 feed water, down to 29.8. So when I thought I was going to get 34.5, because of these conditions, I'm less than 30 pounds per hour, per boiler horsepower. The importance of pressure, also, let's talk about the boiler's sweet spot. We have boilers that we manufacture, various types. They've got figured with various controls and burners and so on and so forth. But every one of those is unique. Each one of those types has its own signature based on horsepower, fuel, burner, and so on. It's got its own signature. It's got its own sweet spot. And that was very, very important. When we understand that particular boiler, we understand the load so that I can select the proper boiler to handle that particular load so it's operating in its sweet spot most of the time. As I said before, we find a lot of boilers out there operating at about 60% of the firing rate. In this particular case, with this boiler, and there's a lot of them out there, and we just took an overall average, is the sweet spot. That's what I want it to run. You don't be running down here or down here, and then cycling a lot, and we'll talk about that as well. want it to be operating at the sweet spot. Find out from that manufacturer, from that sales engineer, if I put this boiler in, where is it most efficient? So I size my load accordingly and keep it there as much as I possibly can. Well, and how do I measure efficiency? Really two methods to measuring efficiency. Either the input-output or heat loss method. Now, if we go to the input-output method, it's more complicated. And quite frankly, in all the years that I've been in this business, and Rakesh will attest to this, who is on the expert panel here, the input method the juice may not be worth the squeeze. You have to go through an awful lot to conduct an input-output test. In other words, it involves parameters, which are devices to be able to determine the amount of moisture in the steam coming out of that nozzle. You also have to have flow meters. It might be a steam flow meter. It could be a water flow meter, because I want to make sure that what is going, I can calculate what's coming out of the boiler, and obviously if I know what's going in, I know what's coming out. Okay, so I can either map my feed water or I can map my steam output. And so I look at stack temperature, I look at the constituents of the gas, I look at my dry gas temperatures, I look at the dry gas, the moisture losses, and so on. That all goes into the input-output method. And what can be very, very precise, it requires a lot of labor, instrumentation, and a lot of complexity. I found over the years that probably the best and most efficient way to go about this is just the heat loss method. And what it does is it takes into consideration what the stack temperature is above the saturated temperature of the boiler itself. It takes into consideration the constituents in that gas, and it also accounts for the moisture losses. So what we're looking for is the temperature, the dioxide, the SO2 is, remember I'm saying we're trying to hold as close to 3% O2 as we possibly can. It'll then give us a net efficiency overall. Say whether or not we've got any carbon monoxide in that gas. If we've got nitrogen oxides, which first nitrogen oxide, NO and NO2 is a precursor to smog, so we want to limit that, especially in places like California and Texas and Louisiana and New Jersey and other places. This stack gas analyzer that you see here will do for us. So it's relatively simple, but when you go through input-output and you compare it to the stack gas analysis, we're often very, very close. So I'd rather lean toward expediency as opposed to something that would be more complex when I'm looking at how I determine my overall efficiency. Now let's look at in-service efficiency. Well, the criteria for that: stack losses, radiant convection losses. What are losses? What do they mean? Settling losses, which really result in purge losses. Turn losses, which is really, we're looking at excess air, and as I said before, most boilers, when they turn down, the excess air rises. Down losses, and the changing load response. What's the change load response? In other words, how effective is this boiler in reacting to load swing? So that's in-service efficiency criteria. So let's look at those. We already addressed the stack losses and the R&C losses, so we'll move right into the startup losses. Losses really assumes that a boiler is offline and it's cold, at ambient temperature. Now, a fire tube boiler, which is a lot of mass, right? It's 5 square feet per boiler horsepower. Again, a vertical boiler right here that has far less mass, let's say. Maybe it's only 2 or 2.5 square feet per boiler horsepower. The whole point is that if I'm starting this boiler to meet load versus this boiler, and they're both at ambient, obviously this boiler is going to heat up faster, and it's going to catch that load faster. No doubt about it. And so an engineer might say, all right, I'm going to put in a bank of these, opposed to 1 or 2 of these. Don't forget one other thing about this. Once boiler comes up to pressure, it's a lot of thermal mass. It's possibly a lot of refractory, a lot of residual heat. So once it comes up to temperature, when that burner cycles off, it can use to steam. Nobody would disagree that a boiler that's not firing is more efficient than anything. really true. These larger mass boilers, once they come up to temperature, hold that heat. And once they start getting swings within the load itself, this will respond just about as quickly as this one. It all depends upon that load. Should I modular, low heating surface, low mass? I go large boiler. Less number, but maybe it's got turned down to match the density would be required for more modular type units. What about cycling losses? I'll tell you, this is one of the culprits as far as loss is concerned, cycling. Whereas have been put in maybe years ago, they still have a lot of useful life. Proper turn down, they haven't matched that load. We've done a lot of things to the process, we've done a lot of things to the building, it's much more efficient, and babies are cycling, turning on and off 15, 20 times more than that an hour. And as a result, we are blowing energy out the stack, we're blowing dollar bills out that stack because of all the cycling losses, cycling on and cycling off. This is where turn down becomes so important too. So maybe you've got an older boiler that's still in very, very good shape. You can retrofit it with a high turn down burner, or keep the same burner but do something with the overall linkage and the way it is controlled as far as the damper is controlled and how it's all configured, and add 10-to-1 to it if it's a 4-to-1 turn down. That can be done. Keep the boiler online. It's like an oxymoron, but actually that boiler staying online is a lot more efficient than having to cycle on and off 15, 20 times an hour. Why is that? The pre- and post-purge losses. Every time that boiler goes down, it has to go through a post-purge loss. Post-purge, you're blowing ambient air through that boiler and chilling it down. Then it goes through a pre-purge before ignition. That's 90 seconds or a minute and a half, blowing air through that boiler. You've got to do that. You want to keep it online. Because blowing is energy out the stack into the atmosphere, heating the ducts. That's all we're doing. And remember, when we're talking about burning fuel, we're talking about burning dollars, cash. Now, losses was also a part of the criteria of in-service efficiency. Yep, continuous blowdown with a boiler. I'm trying to control the TDS level at 1,500 TDS. 100, or maybe it's a bit less, or maybe a bit higher. Our water chemical engineer has advocated a certain water treatment to control total dissolved solids. That boiler is skimming water off the top, and it either goes through a separator and into the sewer, or it can go into a shell and tube heater and recover those BTUs, put it in the feed water before it goes to the deaerator or feed system. Why not reclaim those BTUs? For something. Whatever capture bottom blowdown. Bottom blow is there to be formed once or twice a day, depending upon the chemical analysis and the requirement. Go to a separator and you waste it, because you'll foul with sludge, and so intermittent, as I said, once or twice a day, the juice isn't worth the squeeze in paying for any recovery, really. So bottom blow, don't recover. Surface blow, think about it seriously. What load response? Part of the in-service efficiency. That requires more energy to this big boiler to respond. From a cold start, absolutely right. If you've got a small modular type unit or commercial type water tube product that you see here, these babies respond very, very, very quickly. And based on the characteristics of that load, that's what you need. But don't ever forget that these bigger that you might already have and invested a lot of money in, and you've added controls and burners and so on, can do well too if they're properly controlled and programmed, so that once they come up to pressure, they can run pretty good. Now, I will say that water tube boilers innately will much better than a fire tube will to what I call swing loads, varying loads, because they don't have as much mass, they can respond very, very well. But that doesn't mean that you throw something like this out. It depends on that load, what you have, and what might be done to it to make it respond better. So, recap a little bit. Combustion efficiency takeaway. Stoichiometric combustion is % combustion efficiency. Burn set up with excess air about stoichiometric provides safety, normally 15% excess air. Combustion with consistent excess air throughout the firing range and 0 to a trace of CO, we're talking no more than 50 parts, is considered excellent combustion. So that's the takeaway from combustion efficiency. Thermal efficiency, remember, it does not consider radiation and convection losses. So those BTUs are going into the room that's already 100 degrees. It's not into the process, not going into the hot water to heat that building. All right, what you want to look at is fuel to steam efficiency or fuel to water efficiency. Your takeaways. Insufficiency takeaways. Sites can cost 15% or more in overall efficiency. Never capture the bottom blow, but think seriously about the blowdown heat recovery for continuous blowdown. Response to load quickly is determined by the boiler mass and the water temperature within the vessel. Keep in mind, there are good arguments for modular type leading surface boilers, but also good arguments for a larger mass boiler too. It depends on the application. Obtaining the most efficient boiler system, well, first of all, and I think I've hammered this home, it starts with understanding this load, first of all. Understand the load so I can properly apply the proper boiler for that load, properly sized, with turn down to that load as it varies from low to high fire. Need burner boiler compatibility. Most packages out there today, the engineers have done a good job trying to make these boilers and burners compatible so they deliver the highest radiant efficiency as well as convective heat transfer and radiant heat transfer to give us the highest fuel to steam efficiency. And of course, what also is very important is how do we control these boilers from a burner management standpoint and a combustion control standpoint. Let's get to the single point positioning. Let's go parallel positioning. So I do the hysteresis and the stretch and the slip in those single point positioning linkage arms and rods. Go with individual motorized actuators for the fuel, the air, and if you've got flue gas recirculation because you're trying to limit the nitrogen oxides, the NOx actuators tied into a central control system. So the operator knows all the time what's going on, and we can better control our fuel-air relationship. And eyes for the optimum firing rate. We want that boiler to hang at its optimum. Some boilers might be 60% firing rate, some might be 80, 90% firing rate. Your sales engineer, the boiler manufacturer should know what that is. And if we combine that with turn down so that when we begin to slip off load, we get that boiler on and firing. At what we can improve the overall efficiency of that boiler. Remember, a boiler can only do so much. You get 85% fuel to steam efficiency out of a boiler. It's done about all it can do. If I want to get that up to the above 85%, let's say, I've got to think about external things that I can employ. Blowdown heat recovery I mentioned. What economizer on the stack? A condensing economizer. It could be a standard economizer. If I've got a lot of hot need or 55-degree water and take it through the secondary exchanger and an economizer and bring that water to a tank for whatever potable use might be considered, I can save boatloads of bucks here. I take that fuel to steam efficiency up to the 90% mark. So looking at conserving that valuable resource of oil and gas, the finite resources that come back to us not just as far as the environment is concerned, but come back to us in terms of dollars in the pocket, dollars for the business. We've come a lot today about efficiency and about saving fuel dollars good for the bottom, good for the environment too, as we deplete less of our finite resources of oil and gas and contribute to a positive when it comes to the air that we breathe. So look at efficiency. There's a number of terms out there. There's certainly a lot of confusion. And today, I'll give you some insight on what we talk about, at least when we talk about efficiency. Questions?
Thanks, Steve, very much for that excellent delivery of today's presentation. At this time, please use the question and answer tool on the WebEx control panel and direct your questions to all panelists. As we wait for panel questions to roll in, to introduce our expert panel, sitting alongside of Steve Connor, who very well and will take your questions at the end of today's presenter. We have Rakesh Zala. Rakesh has his master's in mechanical engineering and has been with Cleaver Brooks for over 15 years. Currently, Rakesh is the Director of Product Engineering within our Package Boiler Group. Also at this time, while we're waiting on questions, I'd like to reiterate that today's presentation can be viewed in its entirety. It's archived on our website at cleaverbrookes.com/webinars. You can download the slides if you'd like to have a copy of those as well. And be sure to check out our next presentation for the month of October. It will be Meeting the Industry's Large Steam Needs. And also at the conclusion, as you log off of WebEx, you will receive a short survey. If you would, please take a moment and just give us a little bit of feedback, tell us how we're doing, and we also value what topics you'd like to hear from us in the future. So with that, we'll start taking some questions. We'll let Rakesh and Steve jump in as needed. Our first question we'll take a look at is, will CO and NOx in flue gas at typical levels materially affect the measured combustion efficiency? Thus, is it necessary to measure these for the heat loss method of efficiency testing?
Well, let's take a stab at it first, if I might. You mentioned carbon monoxide, CO, and nitrogen oxides. The NO2 will not figure into the overall efficiency calculation. That's strictly for emissions to those, because those particular constituents are precursor to smog, bad ozone, if you will. But that's not. As far as the CO is concerned, that really would, because what's happening if you're not, if you start to drift to the left of the curve and increase your CO, first of all, it's very dangerous. Carbon monoxide is dangerous. And number two, it's that you're going fuel rich. When you're fuel rich, you're probably going to be sooting the fireside surface of the boiler. Okay, as a result, you're going to be limiting the amount of heat transfer. So therefore, it's going to negatively impact your efficiency.
Okay, and let's look at one. The chart define the various types of boiler burner efficiencies and what they really are. We hope.
I don't know of any particular chart. Maybe Rakesh, do you know of anything that could help this individual?
Yeah, our boiler book should have a few numbers for different burner packages we offer. For example, we have a different fire tube models with different burners. Our book has information, including efficiency for that package.
Okay, that's a good point.
Okay, and I'd like to just point out that the boiler book is located on our website.
It is.
Okay, all right. And let's see, another question. For a new plant with a rapidly fluctuating load, such as brick or dairy, is a water tube generally more responsive and efficient than a fire tube?
I actually would say it would be. All right. Again, it depends upon the load. But in a water tube boiler, the way it is designed, it doesn't have as much heating surface. And those water tube boilers will respond very, very quickly. So if you've got a varying load, it will track that probably better than a fire tube overall. But once that fire tube is up to pressure, it tracks it fairly well. Plus, it has a larger steam accumulation area. So the engineer's got to kind of look at that. The other thing, though, with water tube boilers is, first of all, you can get those in larger capacities and high design pressures. The boiler is going to be limited to about 350-pound design pressure in that area. Water tube can go up to 800-900-pound design. So you may have some operating pressure considerations too, depending upon the application. But to answer your question, I would say yes. A water tube boiler will overall has been designed to track those types of swings.
Okay. And how much heat will the economizer recover for a 300 or 600 horsepower boiler?
How much heat will the
economizer?
Yeah, roughly.
Roughly, a conventional economizer for high-pressure steam boiler will give you around 2 to 2.5% improvement for efficiency. So if boiler is at 80%, with an economizer you can get around 5% efficiency.
That would be a standard economizer.
That's standard economizer.
If they have condensing,
a economizer, if you cold source for the makeup or a processed water, then you can approach 90% total efficiency. So, condensing economizer can give you something like 5 to 7% efficiency improvement, where standard economizer gives you 2 to 2.5% improvement.
And here's another one for you. You mentioned purge losses. What would these purge losses amount to?
Well, these purge losses are going to vary depending upon the operating pressure, but I can tell you, and the ambient temperature in the room, it's all to T. And that boiler is. So that's going to vary, but do you have a rule of thumb as far as purge losses are concerned, cycling losses?
Yes, we do, Steve. The rule of thumb is, if you have a high-pressure steam boiler, 125 pound, 150 pound of pressure, each cycle that you go through, you can multiply the boiler horsepower by 50. So, for example, if you have a 100 horsepower boiler, for cycle, consider you are blowing away 100 times 50, so around 5,000 BTUs per cycle.
Okay. Let's take a look. Deck draft change affect efficiency?
You mean stack pressure? So where will that affect efficiency? Boy.
All right.
See how it affects combustion, but anyway.
Yes, it does affect combustion, but it also has an indirect effect on your efficiency. For example, if you have set up combustion with O2 and the draft changes to negative value or high negative, your 3% O2 can become 4.5% O2. So, because higher excess air, you have lower efficiency.
And that then, Rakesh, might be a good application. If you've got a varying stack, right, a good draft, it'd be a good application for O2 trim, would it not?
That's O2 trim or stack draft control.
Or stack draft
benefit to maintain that excess level and maintain that efficiency.
Okay, good.
All right. Here's one for you. Due to tenant loads, we have lost at least 45% of building load on my 200 horsepower boiler. Normal operating steam range here is 5 to 9 psi. would lowering the operating PSI help my efficiency?
Well, actually, it does. I mean, it's going to improve the overall efficiency because you're not putting as much sensible energy into the pound of water. So, from that standpoint, when you drop your operating pressure, yes, there's going to be some energy savings there. I'm not sure it's going to get you where you want to go, though.
And also, you want to be careful when you drop your operating pressure. You want to make sure your piping, the valves, everything is sized accordingly. Because if the steam pressure is lowered, the specific volume of steam goes up. That means steam velocity goes up. It can have some negative impact on the valve and the pipe sizes that you already have in place.
Excellent point, and that's often overlooked because you see what Rakesh is saying here is the volume of steam increases as the pressure decreases. So flow is to increase, velocity will increase through the piping and across those valves, and it could cause some real serious effect on those valves, especially the valve seats. Yeah, you might want to cut back if you can on the input of that boiler because you're not going to be heating as much. It's decreased there in that particular case. Rather than messing around with the pressure, you want to cut back on your input. The boiler burner combination will tolerate that.
And then you okay.
You do that. One thing, when you do that, you've got to also watch your stack temperature because as you decrease the amount of input, you're going to increase the heating process almost, right? And as a result, your stack temperature could drop and you could start condensing. And that could be a problem for your stack and breaching.
Back to purge loss for a minute. This inquirer says, I have a 100 horsepower boiler for hot water. Is the purge loss the same as a steam boiler?
Well, no. It depends upon the saturated pressure and the temperature, right? Why don't you take that?
Yeah, being a hot water boiler, your bulk water temperature will lower compared to a pressure steam boiler. So it will be lower than a steam boiler.
Okay. Question. I have hot water fire tube boilers that are oversized and fall off during 5 months each year. Would this be a good application for a condensing boiler?
Well, you've got a steam hot water we're talking here, did he say? Hot water? Yeah.
It sounds like the boiler oversized, so it might be a good application to have boilers working in a lead sequence with a large boiler. As far as a condensing boiler, you get a 90+% efficiency on a condensing boiler when your water temperatures are low enough where the gas condense. If your water temperatures are over 150 degrees Fahrenheit, you get enough benefit of being a condensing boiler.
All right, we have a couple of more questions, and we're getting close to time, so we'll start wrapping up here in a few seconds. Does Cleaver Brooks have any products that they do not require as much excess air?
As a matter of fact, we do. In fact, this was meant to be a commercial, though, Susan. But we did develop. As a matter of fact, it was Rakesh's group that developed a line of fire tube boilers that can hold that 3% O2 throughout the firing range. And this has taken a lot of development time and effort to do that. It all boils down to proper control and matching them in the furnace. It's I'll just give the plug. It's the CBEX boiler is what we have on the market today. It's a fire tube boiler with extended surface, and it can maintain that 3% O2 throughout the firing range. But
go down to 10-2 on turn down with 3% O2. And if you remember Steve's charts, where at low firing rate with high excess air, we save 2 percentage point on the efficiency by being able to maintain 3% O2. So it's a big plus having such burner package that can maintain 3% O2 down to 10-2 on turn down.
All right, we're at the top of the hour now. We'll go ahead and wrap things up. If we did not get a chance to get to your question, we can email you back. We have a copy of the questions as they have come through, or you are more than welcome to contact Rakesh Bala, and email address is rzala@cleaverbooks.com, and his contact information is also in the slides should you like to download them from the Cleaver Books website. Again, please take a moment and fill out the survey. We certainly appreciate whatever feedback you have to give us and appreciate topics to let us know what you'd like to hear from us on. Thank you, Rakesh, for sitting in on the expert panel. And as always, Steve Connor, thank you so much for excellent delivery and good information that you have given out to the group. And thank you for being on the expert panel.
You're welcome.
Thank you all, and we